See where we left off in this video, in this class.
Your support will
Usually, as we say that event A, sum of the individual n. Actually solve any problem there is, we can answer any question over 16. And harder question, we get a random point inside hands, then it's a matter of person, would say quite a bit stronger.
Yeah, we got to the second video. Yeah.
Equal
Okay.
to 0 can
Yeah,
happen in many ways. If we get 2 zeros,
Left off here.
is equal to the probability in which we were told that event C occurred. So conditional probabilities do not taste or smell any different than if it in two rolls, so every element die, all possible pairs.
The
Let's
following
start over.
content is provided under a Creative Commons license. Your support will help MIT OpenCourseware continue to offer high-quality educational resources for free. To make a donation or view additional materials from hundreds of MIT courses, visit MIT.
Okay, so let's start with our agenda. The first piece in a probabilistic model is a description of the sample space of an experiment. So we do an experiment, and by experiment, we just mean that just something happens out there. And that's something that happens. It could be flipping a coin, or it could be rolling a die, or it could be doing something in a card game. So we fix a particular experiment, and
I just, okay, that's fine. Yeah.
we come up with a list of all the possible things that may happen during this experiment. So we write down a list of all the possible outcomes. So here's a list of all the possible outcomes of the experiment. I used the word list, but if you want to be a little more formal, it's better to think of that list as a set. So we have a set. That set is our sample space, and it's a set whose elements are the possible outcomes of the experiment. So for example, if you're dealing with flipping a coin, your sample space would be
1 second.
this is one outcome, tails is one outcome, and this set, which has two elements, is the sample space of the experiment. Okay, what do we need to think about when we're setting up this sample space? First, the list should be mutually exclusive, collectively exhaustive. What does that mean? Collectively exhaustive means that no matter what happens in the experiment, you're going to get one of the outcomes inside here. So you have not forgotten any of the possibilities of what may happen in the experiment. Mutually exclusive means that if this happens, then that cannot happen. So at the end of the experiment, you should be able to point out to me just one, exactly one of these outcomes and say, this is the outcome that happened. Okay, so these are sort of basic requirements. There's another requirement which is a little more loose. When you set up your sample space, sometimes you do have some freedom about the details of what you're going to sample. Possible. Well, if you think outside my spaces, some superstitious work, but it's a bit on the frivolous station, and you go to the in order to set up an appropriate sample space. So an easy example now. So of course, the elementary examples are coins, cards, dice. So let's deal with dice, but to keep the diagram small, instead of a 6
Coins, cards, dice.
sided die, we're going to think about the die that only has 4 faces.
Wanted to recap on this. Let's see. Yeah, this thing. So these are just different ways to draw sample space. Remember, a sample space is a set of outcomes. So here's an outcome, here's an outcome, here's an outcome, here's an outcome, here's an outcome. So this is kind of like a general way to draw a sample space. This is kind of like a more structured way to draw a sample space, where like this is an outcome, this is an outcome, this is an outcome, this is an outcome. There's another way to draw a sample space like this, where you do kind of like a tree, where it's kind of like still kind of like a set. It's like where, you know, like this is kind of the sample space. There's an outcome, 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 like that. Sample space. Sample space is a set of outcomes, right?
Dice to set up a probabilistic model. And what are the basic rules of the game for dealing with probabilistic models in more detail? The sample space experiment, more laws, and okay, this experiment happens out there.
Sample space, set of possible outcomes. List or set of possible outcomes. Mutually exclusive, collectively exhaustive.
And that's something that happens, which is 1, 2, 3, or 4. However, the experiment that I'm going to think about will consist of 2 rolls of a die. Crucial point here. I'm rolling the die twice, but I'm thinking of this as just one experiment, not 2 different experiments, not a repetition of twice of the same experiment. So it's one big experiment. During that big experiment, various things will happen, such as I'm rolling the die once, and then I'm rolling the die twice. Okay. So what's the sample space for that experiment? Well, the sample space consists of the possible outcomes. One possible outcome is that your first roll resulted in 2, and the second roll resulted in 3.
Yeah, it's kind of interesting. Like, you know, you could just draw your sample space like, okay, here are the outcomes. It's just like, you know, 1, 2, 2, 1, 3, 2, 4, 1. You know, these are all outcomes. Tuples. But in terms of viewing like the structure of how these outcomes come to be, right now, it's kind of the case that we're just not attributing any structure at all to these outcomes. They're just completely like unstructured. But if we want to like draw this thing in a way that highlights the actual structure of the experiment, we kind of know how these outcomes are generated. We roll the first die, and then we roll the second die like that. And so, you know, 2, 1 is like, so this is like the first die, and this is like the second die. So you could kind of, the first roll, you could kind of, yeah, I guess instead of just kind of drawing all these kind of randomly, you know, like in an unordered thing, you could kind of arrange them in a grid where you kind of say like, okay, 1, 1, 1, you know, 2, 1, 3, 1, 4, 1, like this. And then the first roll is still a 1, so 1, 2. First roll, 2, 2. 3, 2. And you got 4, 2. And then you got 1, 3. And you can kind of like draw, you can think of it as the same kind of whatever like sample space, but instead of them being like all crisscrossed and ordered in whatever order, we've kind of arranged them in a way that reflects some of the structure of how we know that they could come to be, I guess. So you go from like completely unordered of like, 2, 1 up here, 3, 2, 1, 4, whatever, blah, blah, blah. You go from that to this. You can kind of change the shape of the blob too to a square, from like a amorphous blob to like a square, kind of making this more structured. You've got the shape of the sample space. And then you've got the like arrangement of outcomes within the sample space. And so yet another way to kind of organize stuff is that we could, instead of arranging them kind of like this in a grid, we can arrange them in kind of like a list where we go like 1, 2, and we go like 1, we go like 1, 1, 1, 2, 1, 3, 1, 4, where I guess okay, I don't know. I guess this is similar between these two. We are arranging them vertically, but now it's going to be different where we do like, 2, 1, 2, 2, 2, 3, 2, 4 like this. And we kind of, yeah, I guess we can kind of like draw it kind of the same way. Like this is the sample space, and we're just kind of arranging them vertically. And we kind of know that, kind of this one is like the first, we roll like a 1 on the first one. And then depending on the second roll, we roll a 1, roll a 2, roll a 3, roll a 4 like this. And then maybe we roll a 2. Maybe we roll a 2. And then on the second roll, we roll a 1, a 2, a 3, and then a 4. So this is kind of like another way to view the sample space. And I don't know, I guess we could also do it kind of like a grid as well, like a rectangle instead of a blob, because it is more structured. We just arrange them kind of like in a list like this. Yeah. Different ways of drawing the sample space. Different ways of drawing the sample space so that the structure just like pops out. Just pops out like immediately, where you can just see it, where you can just see the structure. You see how different outcomes are related.
In which case, the outcome that you get is this one, a 2 followed by 3. This is one possible outcome. The way I'm describing things, this outcome is to be distinguished from this outcome here, where a 3 is followed by 2. If you're playing backgammon, it doesn't matter which one of the two happened. But if you're dealing with a probabilistic model that wants to keep track of everything that happens in this composite experiment, there are good reasons for distinguishing between these two outcomes. I mean, when this happens, it's definitely something different from that happening. A 2 followed by a 3 is different from a 3 followed by a 2. So this is the correct.
It's kind of cool. It's like programming as well, where you're really just creating a probabilistic model to like solve a particular problem. There is no one perfect probabilistic model, just like there is no one perfect like program or whatever. It's just, does this thing solve the problem that I'm trying to solve, basically? Just like ground yourself in the problem.
Sample space for this experiment where we roll the die twice. It has a total of 16 elements, and it's, of course, a finite set. Sometimes, instead of describing sample spaces in terms of lists or sets or diagrams of this kind, it's useful to describe the experiment in some sequential way. Whenever you have an experiment that consists of multiple stages, it might be useful, at least visually, to give a diagram that shows you how those stages evolve. And that's what we do multiple stages. It's of this kind. It's useful to describe the experiment in some sequential way. Whenever you have an experiment that consists of multiple stages, it might be useful, at least visually, to give a diagram that shows you how those stages evolve. And that's what we do by using a sequential description or a tree-based description by drawing a tree of the possible evolutions during our experiment. So in this tree, I'm thinking of a first stage in which I roll the first die, and there are 4 possible results, 1, 2, 3, and 4. And given what happened in the first, let's say in the first roll, suppose I got a 1, then I'm rolling the second die, and there are 4 possibilities for what may happen to the second die, and the possible results are 1, 2, 3, and 4 again. So what's the relation between the two diagrams? Well, for example, the outcome 2 followed by 3 corresponds to this path on the tree. So this path corresponds to 2 followed by a 3. Any path is associated to a particular outcome. Any outcome is associated to a particular path. And instead of paths, you may want to think in terms of the leaves of this diagram. Same thing. Think of each one of the leaves as being one possible outcome. And of course, we have 16 outcomes here. We have 16 outcomes here. Maybe you noticed a subtlety that I used in my language. I said I roll the first die, and the result that I get is a 2. I didn't use the word outcome. I want to reserve the word outcome to mean the overall outcome at the end of the overall experiment. So 2, 3 is the outcome of the experiment. The experiment consisted of stages. 2 was the result in the first stage, 3 was the result in the second stage. You put all those results together and you get your outcome. Okay, perhaps we are splitting hairs here, but it's useful to keep the concepts right. What's special about this example is that besides being trivial, it has a sample space which is finite. There's 16 possible total outcomes. Not every experiment has a finite sample space. Here's an experiment in which the sample space is infinite. So you're playing darts, and the target is this square, and you're perfect at that game, so you're sure that your darts will always fall inside this square. So, but where exactly your dart will fall inside that square, that itself is random. We don't know what it's going to be. It's uncertain. So all the possible points inside the square are possible outcomes of the experiment. So a typical outcome of the experiment is going to be a pair of numbers, x, y, where x and y are real numbers between 0 and 1. Now there's infinitely many real numbers, There's infinitely many points in the square. So this is an example in which our sample space is an infinite set. Okay, so we're going to revisit this example a little later. Okay, so these are two examples of what a sample space might be in simple experiments. Now, the more important order of business is now to look at those possible outcomes and make some statements about their relative likelihoods. Which outcome is more likely to occur compared to the others? And the way we do this is by assigning probabilities to the outcomes. Well, not exactly. Suppose that all you were to do was to assign probabilities to individual outcomes. If you go back to this example and you consider one particular outcome, let's say this.
Yeah, I know where he's going with this. So I don't think we kind of did this last time, but yeah, we're talking about probabilities of events. And we say like the probability of, just like the event of the set containing, 0.5, 0.3 like this. This is going to be equal to 0. And in fact, the probability of any finite, any like finite set of points is equal to 0. Like if you can write it like this, where you can just like list out the numbers and it's got a start and it's got an end, then yeah, the probability of that is 0. So you can't really like list out all the outcomes. You can't really like arrange them in this form. You really have to kind of draw this. You don't have to draw the sample space like this, but it's it's probably the most natural way to draw it. It's raining hard here.
What would be the probability that you hit exactly this point to infinite precision? Intuitively, that probability would be 0.
I'm gonna jump off, by the way. I gotta do this event. See you guys. Peace.